Okay, for this part, we have what is regarded as least squares regression analysis. And we have from your textbook, it has of all possible linear models for a given set of points, the model that has the best fit is the one that minimizes the sum of the squared error. And it says that this model is the least squares regression line, and the procedure for finding it is what is referred to as the method of least squares. And we have, by definition, for a given set of points, in the xy coordinate system, the least squares regression line is the linear function where we have y, or f of x, is equal to a naught plus a of 1 times x. That is going to minimize the sum of the squared error. And we'll be looking at determining the least squares regression line through the use of matrices. But first of all, I just want to give you a statistical example. Now, it's going to be a bit analytical, so just bear with me. Let's say that through a statistical analysis, if you have to determine the equation for the least squares regression line, and say we have three given points where we have negative 1, 1, 1, 3, and 2, 10. And so we had the number of points n is equal to 3. And through statistical analysis, you're going to start out by taking the mean value of the x and y coordinates. And so for what we have for the mean in x, the x with the bar over it, you're just looking at adding up the x coordinates and dividing by the number of points. And in this particular case, you have negative 1 plus 1 plus 2 comes out to 2, and then we have divided by n, which is 3, and 2/3 is already in simplest form. Likewise, for the mean y value, I'm adding up the y coordinates 1, 3, and 10, and we have already in simplest form, we have the mean y value is already at 14/3. And after attaining the mean, we'll be looking at the attainment of sample standard deviations for the x and the y terms. And just lining up what we have here, for the sets of x and y values. So you're going to be taking differences between x one at a time and the mean value, which you have at 2/3 throughout. So if I have x minus the mean value, you have like for x at negative 1, the difference is at negative 5/3. X at 1, you have 1 minus 2/3 is 1/3, and 2 minus 2/3 comes out to 4/3. And squaring each of the differences, so I have 25 ninths, 1 ninth, and 16 ninths. Now, if I take the sum of these values, I come out to 42 ninths, and so we had the reduction down to 14/3. Now, for what I have in y, again, you had the y values at 1, 3, and 10, and the mean y value, which we just attained at 14/3, we're going to be utilizing in the process of taking this amount away from each of the y values. So for 1 minus 14/3, we have minus 11/3, then 3 minus 14/3, which we have at negative 5/3, and then we have 10 minus 14/3, or 30/3 minus 14/3, which will be 16/3. And squaring these differences, so I have 121 ninths, 25 ninths, and 256 ninths. Now in ninths, we have 402 ninths, and for the sum of the square of the differences, we had the reduction down to 134/3. And for the sum of the squares of the differences, we're going to be able to attain the sample standard deviation for what we have in x and y. Now for what we have starting out with the sample standard deviation of the x values, we're going to have the square of this equal to the sum of the squares of the differences we just attained divided by the number of points minus 1, or the number of elements involved minus 1. So n was at 3, and 3 minus 1 is 2, and the sum of interest we had at 14/3, and we have the square of the sample standard deviation in x we have at 7/3, and taking the square root, that is going to be the sample standard deviation for what we have in x, which we can express as either the square root of 7/3 or the square root of 21/3. Now for the sample standard deviation that we have in y. Now the square of the sample standard deviation, again, you have the sum of the square of the differences in y. Okay, so you have between y and the mean value, so you had, again, 134 thirds, and dividing by number of points minus 1, which we have at 2, and this lowers to 67 thirds. And then taking the square root of 67 thirds and just rewriting, we can express either as the square root of 67 thirds or as the square root of 201 over 3. Now, we're going to be looking at involvement, okay, between the differences and the respective sample standard deviations. Okay, so again, we had x minus the mean. Okay, just going back to what we had from earlier, as well as y minus the mean. So I'm going to put these column values back up, and I'm going to take each of the differences and divide by the corresponding sample standard deviation. Here, again, the sample standard deviation we had at the square root of 21 over 3. And if I divide negative 5 thirds by the square root of 21 over 3, and simplifying, okay, we have negative 5 over the square root of 21. Then 1/3 in the difference divided by the standard deviation in the sampling for x. We have 1 over the square root of 21, and then we have 4 over the square root of 21. And again, for the differences we had in y with negative 11 thirds, negative 5 thirds, and 16 thirds, if I divide these differences by the sample standard deviation in y, in other words, it's going to be multiplying by 3 over the square root of 201. So I have these values, negative 11, negative 5, and 16, all of these each over the square root of 201. And if I look at now with the differences over the corresponding sample standard deviations, okay, so for the second column and the fourth column values, if I multiply together, I'm looking at the attainments of this product. So you have like negative 5 times negative 11, you have 55, and the square root of 21 times that of 201. Okay, this would simplify to 3 times the square root of 469. And just following through in the same fashion, so I got negative 5 over the same denominator. Okay, and we have 4 times 16 is 64. Again, we have all over 3 times the square root of 469. And taking the sum of the products, and in this particular case, all right, so I have 55 minus 5 is 50, plus 64 is 114, and divided by 3 over the square root of 469. So this will come out to 38 over the square root of 469. Okay, now for what we have in terms of the value of r, and for what we have in the case of r, okay, so we have 1 over n minus 1, and you have times the aforementioned, okay, summation of the products we just looked at. Okay, so you have, again, you have 1 over 3 minus 1, which is going to be 1/2, and you have times 38 over the square root of 469, okay, and so half of 38 is going to be 19, and we have 19 over the square root of 469. Okay, so R, okay, this is going to be what is referred to as the correlation coefficient. Okay, so the correlation coefficient, again, is 19 over the square root of 469. Now, going back, okay, to developing, okay, the equation of the least squares line. Okay, so we have for what is referred to as A of 1, we're looking at the product of the correlation coefficient and the ratio, where we had the sample standard deviation of y over the sample standard deviation of x. Okay, so this, again, we have r at 19 over the square root of 469, and we have times the sample standard deviation in y. Again, you have the square root of 201 over 3, and then dividing by the sample standard deviation in x, or multiplying by the reciprocal again. So you have the 3's here to cancel out, and now we got 19 times the square root of 201 over 9849, and this ratio reduces to 149, and so we have 19 times 1/7, so we have A of 1 comes out to 19 over 7. And for what we have in the case of A naught, okay, so in the statistical development, okay, we're looking at the mean value of y minus, the value of a of 1 times the mean that we had in x. And so we have 14 thirds minus 19 sevenths times 2 thirds. And narrowing it down, so you have 14 thirds minus 38 over 21, and that is equal to 20 sevenths. So we have for the equation in this particular case, all right, so you have, again, y is, or f of x is equal to a of 1 times x plus a naught, and specifying we have y is equal to 19 sevenths of x plus 20 sevenths. Now if we look at defining y, x, a, and e in matrix terms, then the nlinear equations that we have can be replaced by the matrix equation. We have y is equal to x times a plus e, and e is just in reference to the errors involved, like the sum of the squares of the error sizes. And now for the same three order pairs we just looked at, and we can apply a matrix type situation and come out to the same results. Okay, so for a little bit of history repeating, it says to determine the equation for the least squares regression line. And this time we're going to be using matrices. And so for matrix X, again, I'm going to have the first column to consist solely of the value 1. And the second column, I'm just going to input the x coordinates where I have at -1, 1, and 2. And for y, I have the y coordinates where I have 1, 3, and 10. Now, setting things up, now I'm going to take the transverse of x times x itself. Now the transverse, again, you have 1, 1, 1 at the top, and then we have -1, 1, 2 on the bottom. So you have a little interchange between the row and column positions, and multiplying by x, and just with the numbers, just kind of going back. And you can use your calculator to attain the product, but again, just in the procedure. Okay, so you have the second column of x multiplying what we have in this particular case. All right, so we have in the arrangement. Okay, so for the transverse of x times x, looking at the procedure, just kind of like what we did in the earlier parts of chapter 2, we come out to, for this product, we have 3 and 2 at the top, 2 and 6 on the bottom. And then we have for the next item, we're looking at the transverse of x times y. And following through in similar fashion, okay, we come out to, in this case, a 2 by 1 matrix where we have 14 and 22. And now we're looking at, again, what's going to be the coefficient of a. And this is going to involve taking the inverse of the product of the transverse of x times x. Okay, so again, the transverse of x times x, we have 3, 2, 2, and 6. And just looking at what we have in the layout. Okay, so you have 3, 2, 2, 6. I'm going to put in an identity matrix where the values you have 1, 0, 0, 1, and just translating 3, 2, 2, 6 in identity terms. So we have in the proceedings, so if I take 1/3 of the first row, I got 1, 2/3, 1/3, and 0. And then we have for the second row, if I take R2 minus twice R of 1, so we have 0, 14 thirds, -2 thirds, and 1. And then we have 3 14ths of the second row. So we have 0, 1, -1 seventh, and 3 14ths. And getting to the stage of the completing out with the Gauss-Jordan elimination, I'm going to take the top row and deduct 2/3 of the second row. So the top row we have 1, 0, 3 sevenths and -1 seventh. Bottom row, again, we have 0, 1, -1 seventh, and 3 14ths. And guess what? What I have with the last two columns, this is going to make up the inverse of the product of the transverse of x times x. And so for what we have in this particular case, all right, so the inverse of the transverse of x times x, I have this 2 by 2 matrix. And again, for the transverse of x times y, again, I have 14 and 22. And following through, multiplying, and we come up with the two numbers of 20 sevenths and 19 sevenths. And for what this is going to signify is that we have for y, guess what, the 27th is going to be the constant. And for the coefficient of the x term, okay, this will be from the bottom value of what I have in the matrix A. So we have 19/7 of x. And you can put this in slope-intercept form where we have formally declaring that y is equal to 19/7 of x plus 27. Okay, and just looking at what we have here for the model of best fit, and you have this red line in the graph, okay, where we have 19/7 of x plus 27, and this is going to be the best fit. Now, if I'm looking at the equation for the least squares regression line, okay, and we have given these 5 points, again, for the matrix X, again, the first column I have exclusively ones, second column I have the X values, -2, -1, 1, 2, and 4. And again, for the Y matrix, I have exclusively the corresponding Y values. And again, just going through the proceeding, if I take the transverse of X times X, I come out to 5, 4, 4, and 26. And then for the product of the transverse of X times matrix Y, I'm going to come out to 17 and 52. And then looking at taking the inverse of the product of the transverse of X and X. And what's going to happen here is that throughout all the proceedings, okay, and again, you can arrive at it through the use of the calculator, but again, be careful with your calculating device, okay? And the inverse, in this case, we have with the fractions, 13/57, -2/57 at the top, and then we have in the denominator, I have -2/57 and 5/114. And then looking at what we have for the coefficient matrix A, we're going to get through the middle once again. So you have the just attained inverse of the product of the transverse of X times X. Again, so I have this same 2 by 2 matrix, and again, multiplying by the matrix resulting from multiplying the transverse of X times Y. Okay, so I have the 2 by 1 matrix with 17 and 52, and we have for the outcome, we have 39/19, and for the slope of the regression line, we have a 32/19. And so we have, and you can write it either two ways, where we can say that y is equal to 39/19 plus 32/19 of x, or in the traditional slope-intercept form, we have y is equal to 32/19 of x plus 39/19. And just looking at how this line is going to appear,